The purpose of this podcast is to show you how to find the zeros of a polynomial function. Sometimes we call it finding the roots of a polynomial function. And it's just another way of saying we have a polynomial equation that we're trying to set equal to 0, and we're trying to find all the values of x that would make that equation true. You might have a question like this or a problem like this in a college algebra class. In high school, it would either be in an Algebra 2 or a pre-calculus course. The methods that I'm going to use today include the rational zero theorem, Descartes' rule of signs. I'm going to use synthetic division and the quadratic formula, all to solve this equation, as well as using the graphing calculator to visually see those answers as well. First of all, a polynomial function is one that has exponents that are integer values and they are positive. You can also have an x to the 0 power as well, which gives you your constant term, but you're not going to have negative exponents or fraction exponents. Now, you might encounter a problem like this. Let's say that this equation was, let's say it had a plus 12 on the end, and it was equal to 13. Maybe this equation stands for the profit of a company, and we want to figure out when it's equal to 13 million. Well, if you think back to the equations that we solved in Algebra 1 and Algebra 2, if I were solving a quadratic, a lot of times we will set it equal to 0 so that we can factor it and use the zero product property. The same methods are going to work here. If I had a polynomial equation equal to a number, I would subtract that number over and have it set equal to 0. That way, when I solve it, I'm looking for the numbers that would go in the place of x that make this equation equal to 0, and it gives us the opportunity to use the zero product property. So the methods that work for solving quadratics will also work here. Usually the one that we want to use is factoring. It doesn't always work, and in this case it won't until we get it down further. But if we get it down to a quadratic, we'll also want to use quadratic formula. All right, first thing that I would do to solve this problem is list out all the possible rational zeros. And the rational zeros are going to come from the quotient of p over q. P are the factors of the constant term, and q are the factors of the leading coefficient. So the factors of -1 are 1 and -1. Oops, I don't need that. Okay. And the factors of 2 are plus or minus 1, plus or minus 2. When I divide these out, I end up with plus or minus 1 over 1 and plus or minus 1 over 2, which really gives me 4 possible numbers that could be the rational answers to this polynomial: 1, -1, 1/2, and -1/2. Now, it is possible that we're going to get irrational answers, and they wouldn't come from this list. It's also possible that we could get complex answers. They also won't come from this list. The next thing I like to have my students do is try to figure out what kind of answers we're going to get by using Descartes' rule of signs. And Descartes' rule of signs, to figure out what the positives are, we look at the signs of the coefficients in the problem right now. 2 is positive, 15 is positive, 17 is positive, 3 is positive, and 1 is negative. And what we want to do here is figure out how many sign changes are there from left to right. So starting with the positive, we go to another positive until we get to this last one. And that's one sign change from positive to negative, which means there's one positive 0. Now, to figure out the negatives, we need to evaluate the polynomial with the opposite of x in its place. There's some shortcuts for this. But what we have to do is substitute x with negative x, opposite of x, 2 times the opposite of x to the 4th power, plus 15 times the opposite of x cubed, plus 17 times the opposite of x squared, plus 3 times the opposite of x minus 1. Now, if we simplify this expression, we remember that anything to an even power, the negative will square out or will become positive again. And so I'll end up with 2x to the 4th. With an odd power, it won't though. I'll pull that negative to the front, plus 17x squared minus 3x minus 1. And now my signs are plus, minus, plus, minus, minus. That gives me a sign change in between the first and second coefficient, the second and the third and the fourth, which means there are 3 negative zeros. Or Descartes also allows for the possibility that there could be 2 of them that are imaginary, which means there could be either 3 or 1 negative zero, real zero. Okay, and that would be an example where the graph would look something like this. Your graph could cross 3 times on the left-hand side and once on the right. Or your graph could just cross once on the left-hand side and once on the right. So this loop right here, if it's moved down, you're going to lose 2 of those possible real zeros. Okay, so now what have we done so far? It looks like we've done a lot of work. We've listed out the possible rational zeros. We've listed out what kind of answers we're going to get. Now, could you do this problem without doing all this work? Yes, but when you get good at this, it doesn't take very long. So it really helps you get an idea of what kind of answers you're going to end up with. Okay, now we've got a list of possible answers. We need to make a guess as to one of the possible numbers that could work in this polynomial. So go back to the plus or minus 1 half, make a guess. We know one of the answers is going to be positive, 3 of them, or possibly one of them is going to be negative. Now I'm going to try a negative one to begin with because I like the idea that 3 of the answers could be negative. So let me move this down. I'm going to take this original polynomial and I'm going to do some synthetic division here. 2, 15, 17, 3, negative 1. And I'm just going to randomly guess one of the numbers from my list. I'm going to try negative 1. Okay. So with synthetic division, I first drop down the first number 2. I multiply by negative 1 to get negative 2. Add with the 15 to end up with 13. Multiply by the negative 1 to get negative 13. Add with the 17 to get 4. Multiply to get negative 4, add with a 3 to get negative 1, multiply with negative 1 to make 1, and I end up with a remainder of 0. Now this is important because it tells us that negative 1 is a 0 to this function. We now have one of our 4 answers. Next thing I always tell my students is to look at what's left over and to write it as a polynomial. 2x cubed plus 13x squared plus 4x minus 1. And because it's a 4-term expression, ask yourself if it will factor by grouping. And unfortunately, this one won't. So we need to go back to the list and guess another number that could work now in this polynomial of degree 3. I'm going to try that other negative, which was negative 1/2. Okay, drop down the 2. Multiply, add together, multiply, add together, multiply, add together. And negative 1/2 is a 0. Now, both of my first two guesses worked. It's possible that you might have to guess and you won't get it on the first couple tries, and that might seem a little bit frustrating, but you just got to keep trying. All right, now I'm going to take my leftover here and write it as a quadratic. 2x squared plus 12x minus 2. There's a lot of different ways to solve a quadratic. My first thought is I'm going to try to factor this, and I notice that all of these are a multiple of 2, so I'm going to take that 2 out. And I'm going to ask myself, can I factor what's left over? Can I think of anything that multiplies to be negative 1 that adds to be 6? It's not going to work. So my next step would be to use the quadratic formula on the trinomial that's inside parentheses here. Okay, don't worry about the 2. We're just going to work with the coefficients 1, 6, and negative 1. So I want the opposite of 6 plus or minus the square root of 6 squared minus 4 times 1 times negative 1 all over 2 times 1, which gives us negative 6 plus or minus the square root of 36 plus 4 all over 2, and negative 6 plus or minus the square root of 40 all over 2. Now, square root of 40 is the same thing as square root of 4 square root of 10, which makes 2 square root of 10. So I have negative 6 plus or minus 2 square root of 10 all over 2. And negative 6 divided by 2 is negative 3. 2 root 10 divided by 2 is 1 root 10. I don't need to write the 1. Okay. So now, backing up, I've got solutions negative 1, negative 1/2, and negative 3 plus or minus the square root of 10. And this is what I would write. The zeros, or the solution of this polynomial. Okay, those are the exact answers. Now, you're certainly welcome to change the negative 3 plus or minus square root of 10 to a decimal, if that makes sense in your problem. Negative 3 plus the square root of 10 is approximately 162 thousandths. Negative 3 minus the square root of 10 is approximately negative 6 and 162 thousandths. So really we end up with one positive and one negative from that quadratic formula. So let's see if Descartes was right. We have one negative here, and then the negative 6 and 162 thousandths was our third negative, so that was this one. So we had 3 negatives. And the negative 3 plus the square root of 10 was the positive 162 thousandths, which was our one positive. So Descartes was right. Now, one thing that the graphing calculator can help you do here, to save a little bit of time, you could type the function into the y1 and then graph the equation. And I like to do this on problems where it has a lot of zeros and I just want a lot of possible rational zeros and I just want to save time. I would look at this and try to get an understanding of where my answers are. Looks like there's one, let's see, around negative 6. It doesn't look like it's exactly negative 6. That looks like negative 1. There's my negative 1/2, and then that's that positive 162 thousandths. If you want to know for sure, go to your table of values. Oops. Sorry. And just look to see what the table shows you. The table does in fact show you that negative 1 is a 0, so that's a good guessing point to start off with. It'll also show you, if you use the intermediate value theorem, where the rest of the zeros are. The intermediate value theorem says that if you have a change in sign in your y values, for example right there, from positive 468 to negative 55, then that tells you that you have a 0 in between those two x values, which in fact we do. All right, that's the end of this problem. There's a lot of steps to these problems. And you certainly are going to use things like factoring and quadratic formula and Descartes' rule of signs, but in the end you will find the solutions to the equation. Thank you.